Okay, so today we will look at module 4, which is assembly language programming. Okay, so starting from today onwards, okay, we're looking at how to write a program in assembly language. Okay, for the uh, first few slides, okay, I will skip this one here. Okay, you can read it by your own actually. Okay, so this one also you can read by your own. Okay, up until okay, because this is only on the overview of the AVR System Software. Okay, which is it cover on what is machine language, what is assembly language, what is the high level language, and the disadvantage of high level language, assembly language, and machine language, and etc. Okay, and then for the AVR system programming, this one also you can read it by your own. Okay, so in this one, in this subchapter here, you will learn about the emulator, what the emulator do, and then you can learn about what is a simulator, okay, and then what the simulator do, and then you have a debugger, disassembler, and etc. Okay, now I want to focus on how to write the assembly program. Okay, so as we know that assembly language is a low-level program that deal with the internal structure of CPUs, all right, which provide minimum for machine code instruction. Okay, means that okay, so this is the what we call the pyramid of the uh, programming language. Okay, as we can see here, the bottom here it is your hardware, and then followed by the machine language. Okay, this machine language here is this one here only can interpret by your computer lah, your CPU. You cannot know what's the the what we call here, what is the value, okay, the value of each of the machine language or each of the machine code. You cannot know what that instruction do. Okay, and then after that we have an assembly language. Okay, so this is the low level language lah. Okay, and then followed by the HLL, high level language, which is consist of C programming, C++, you have a Python, you have a Pascal, Fortran, Java, and etc. Okay, so to program in assembly language, the programmer must know all the register of the CPU and size of each, as well as other details. Means that in order to write an assembly language, you need to know your hardware design. Okay, you need to know the hardware architecture. Okay, means that you need to know, okay, for the hardware, how many input output that available in that hardware. Okay, and then how many registers, okay, inside of that CPUs, okay, that available inside of CPU. What is the size of your RAM? What is the size of your flash program? Okay, flash memory. Okay, you need to know all those things before you write down in the assembly language. Okay, so assembly language must be translated into machine code by a program called assembler. Okay, after you did the what we call here, the after you write down your assembly language, okay, to translate to machine language, we will need to use the assembler. So an assembly language program is a series statement of all lines which are either assembly language instruction or a statement called directive. Okay, so in assembly language, we can divide it into two parts. The first part we call it as an instruction, okay, which is this instruction will tell the CPU what to do. Okay, and then we have the second part here is the directive. Okay, so this one here, it will give direction to the assembler, which is it will translate the assembly to machine code. All right, so this is the instruction of your assembly language, which is consists of a label, mnemonics, operand, and a command. Okay, so this one here we already learned in the previous slide. in the previous class. Okay, now in this module, we want to focus on the what we call here the directive part. All right. So this is an example of the assembly language. Okay. So if you can see here, this assembly language, okay, consists of two parts. One part we call it as an instruction, the other part we call it as a directive. Okay, how do you want to identify which one is the instruction, which one is a directive? Okay, so to identify which one is instruction part, which one is a directive, okay, we can look at the instruction itself. Okay, for example lah. Okay, so every time you see the dot here, okay, so this one here belong to directive. Okay, you see the dot and then followed by the mnemonics. Okay, so this one you know that this is belong to your directive. Okay, other than that, okay, this one here, this is the basics instruction. Okay, which is consist of LDI that we already learned in the previous class, ADD for example, STS, and then you have a JMP. Okay, so this is another instruction. Okay, so this is how we want to classify to differentiate between a directive and instruction of the assembly language. Okay, so in the next few slides, we will learn more on the assembler directive. There are a lot of assembler directive that you need to know. Okay, instead of the org and dot equ, because this one here, this is the common punya directive lah that we usually use. Okay, while the instruction tell the CPU what to do, okay, the directive will give the direction to the assembler. Okay, so this directive actually help us to develop our program easier and make our program more readable. Okay, that is the function of the directive. Okay, why? It will help to develop our program easier and readable. Okay, so this is another example kat sini. We have this is your program, okay, assembly language program. Okay, if you can see here, okay, at the top of this program here, you can see this is a directive part. Okay, this is your directive part. Okay, how to identify the directive? Okay, by looking at the instruction. Okay, you can see here it's starting with the dot. Okay, every time you see the dot in front of your mnemonic or in front of your instruction, this one belong to your directive. Okay, this directive, dot byte, dot org, dot dset, dot include, dot eq. This is the directive part. Okay, other than that, so this one here belong to your instruction part. Okay, ada soalan tak up until here? This is how we want to differentiate between the directive and instruction. Ada soalan? Okay, if not question. Okay, let's look at the first assembler directive. Okay, so this one here. This one we call the first one here we call it as a dot dset, which is it is a data segment. Okay, so the dset directive define the start of your data segment. Okay, so this one here will define the start of your data segment. So an assembler file can consist of several data segments which are concatenated into one data segment when assembler. Okay, a data segment will normally only consist of byte directive. Okay, so this is the first one here. Okay, actually our directive, okay, this directive here can be divided into three parts. Okay, kita boleh bahagikan dia kepada tiga bahagian. Okay, the first part we call it as a dset, which is your data segment. Okay, so this data segment here actually belongs to your RAM. Okay, and then we have the ESEC. Okay, so this one belong this is the EEPROM segment. Okay, so this one belong to your EEPROM, and the third one here we call it as a CSEC. Okay, this one here belong to your program memory or flash memory. Okay, so this directive can be divided into three more parts, which is a data segment, which is the data that inside of your RAM, E segment, okay, which is inside of your EEPROM, and the last one is your CSEC, which is inside of your flash or program. So in this case here, okay, under the CSEC, okay, you will put all of your, what we call here, all of your programming, because this instruction here will be stored to your flash or program memory. So you need to make sure that all of this instruction here that you write, okay, all of your programming here that you write must be put under the code segment. Okay, so the .dset is for the data segment. Okay, so this one here belong to your RAM. Okay, the data inside of your RAM. Okay, so inside of this .dset, you need the directive that you can use is byte only. Okay, and you cannot use what we call the directive that you can use is .byte and .org. Okay, other than that, you cannot put any of the instruction. Okay, so and then next we have the .csec. Okay, so this one yes, this belong to your code segment. Okay, the csec directive define the start of your code segment. Okay, an assembler file can consist of several code segments which are concatenated into one code segment when assembler. Okay, the byte directive, which is your .byte, cannot be used within your code segment. Okay, so the default segment type is a code, which is your program lah, your instruction. Okay, so this code segment have their own location counter, which is a word counter. Okay, so this is the dset. You have the data segment, and then you have the C segment. Okay, this is for the code segment, which is consist of your instruction. Okay, your programming inside here. Okay, so all your programming and instruction must be put here. You cannot put .byte under this code segment, or you cannot use, you cannot put the instruction, all of this instruction or programming under the data segment. Okay, and last but not least is your ESEC. Okay, so this is for the EEPROM segment. Okay, so this one here, the ESEC directive define the start of your EEPROM segment. Okay, and then an assembler file can consist of several EEPROM segments which are concatenated into one EEPROM segment when assembler. The byte directive cannot be used within the EEPROM segment, so you cannot use the .byte inside of this ESEC as well. Okay, so the .byte only can be used under data segment. Okay, and your programming, all the instruction also cannot be put under this ESEC. Okay, so this is the example that we look earlier. Okay, yang kita tengok sebelum tadi. Okay, next. Okay, that is the segment that you need to know. You have three segments under the directive: data segment, code segment, and EEPROM segment. Okay, so in this class, in this course, we only focus on these two here: data segment and code segment. While the EEPROM, we can what we call here, we can. Okay, we no need to focus on that EEPROM segment. Okay, so let's look at another assembler directive that available in AVR. Okay, this is the command that we will use, okay, in our programming, which is .equ. Okay, so this .equ will set a symbol equal to an expression. Okay, so this EQ directive assign a value to a label. Okay, means that you don't want to use a numbers. Okay, you don't want to use a value. Okay, instead you can replace it with a name, or you can replace the value with the label. Okay, but this label here, this name here, the value cannot be changed and redefined. Okay, this label can then be used in a later expression. Okay, but the constant or the value that you put to this EQU cannot be changed or redefined. Okay, for example, let's look at this example here. Okay, dot EQU, okay, and then this is your label, this is your name, IO underscore offset equal to OX23. So every time you see the word, the label IO underscore offset, you know that this label here will have value 23. Okay, so setiap kali kamu jumpa IO underscore offset, this one here, you know that this is 23. Okay, and then we have another one, dot EQU port A equal to IO underscore offset plus 2. Okay, you know that every time you see the word port A, it equal to IO underscore offset plus 2, which is 23 plus with 2. Okay, so that is your port A. So every time you see the port A, so the port A value is 25. Okay, so this is inside your code segment. Okay, under the code segment, okay, you see the clear R2. Okay, what you're going to do here, you clear your R2, your GPR R2. So R2 will be kosong, akan jadi kosong. And then out port A R2. What is it actually? Okay, you're going to send out the value of R2 to the address point, okay, to address port A, which is what address here? OX25. Okay, so instead of using the what we call here the value or the constant, okay, you replace it with a name or label. Okay, so this is what the .equ do lah. Okay, so again, this .equ is used to define a constant value or a fixed address. Okay, you can replace the you can replace the value with a label or a fixed address also with the others name. Okay, so let's look at this example here. The following use .equ for the counter constant, and the constant is used to load to the R21. Okay, for example, .equ count equal to OX25. Means that every time you see the word count, you know that the value is 25. So below here, okay, and then you have the programming. Okay, then you see the load IR21 count. So you know that the count here is 25. So what happens is, after you execute this instruction, you want to load 25 to your R21. So that's why after you execute this instruction, what happens is your R21 now become OX25. Okay, so as mentioned in the previous class, okay, we can use the name of the IO register instead of their addresses. Okay, so you recall back, okay, we can use the out port B R20 instead of out the address R20. Okay, why can we can use the name of our IO register? Okay, because okay, this one here, okay, the reason why we can use the name of our IO register, okay, instead of memorize the what we call here the IO address, because we okay, this one here, because we have the .equ directive inside of this file here. Okay, so we already defined each of the IO addresses with the IO register name inside of this what you call here file, okay, called amplitude.def.inc. Okay, so In the empty2def.inc, the following directives exist which associate with, for example, we looking at this example here, we know that, okay, for this port B, okay, instead of using the OX1B address, we just use the name out port B R20. Why? Because inside of this empty2def.inc, okay, this following directive .equ port B equal OX1B existed. Okay, that's why we can use the name port B name instead of memorize the IO addresses. Okay, then that is for the .equ lah. Okay, .equ means that you want to change the constant or you want to change the address to a label or to a name. Okay, then we have the .set. Okay, so this .set used to set a symbol equal to an expression. Okay, so the .set directive assign a value to a label. Okay, this is similar to EQU. Okay, dia sama juga dengan .EQU. Okay, but there is a but. This .set directive can be changed later in the program. Okay, so you can change the value of this of the label later in your program. Compared to .equ, okay, once you saying that, contoh lah, you saying that the .equ IO underscore offset equal to 25. Later, if you going to change to .equ IO underscore offset to 30, for example, you cannot do that. Okay, because this one here, you cannot, for the .equ, you cannot change later in the program. Compared to .set, okay, for example, at the top of your program, you saying that .set IO underscore offset equal to 23. Okay, next, you want to redefine this IO offset to 30, for example. Okay, so you just put .set IO underscore offset dot 35. So the value that the program will take is the latest value after the CPU execute this instruction, which is 25. Okay, for example kat sini, .set IO underscore offset equal to OX23. So what happened here? So every time you see the word IO underscore offset sama dengan 23. And then .set port A equal to IO underscore offset 23. So you know that port A now become equal to 23 plus 2, which is 25. Okay, and then later on, okay, if you see, every time you see the port A and then IO underscore offset, you know that this is the value. It equal to .equ, but this one here, the .set, you can redefine or you can change later in the program. Okay, next we have the .include. Okay, so this .include used to include another file. Okay, you want to import another file to your program. Okay, to import another file, to include another file to your program, so we need to use the .include directive. Okay, so this .include directive tells the assembler to start reading from a specific file. Okay, the assembler then assembles the specific file until the end of the file, which is E or F, or an exit directive is encountered. And an included file may itself contain include directive. Okay, for example lah. Okay, so this is your file. So this file here named iodef.asm. Okay, so this is the file named iof.asm. So inside of this file, okay, you initialize, okay, you equate all of this label to a value. Okay, for example, dot equ srec equal to 3f, dot equ sp high equal to 3e, and then dot equ sp low to 3d. Okay, so you save the file. Okay, later you write a program. Okay, so you write a program. Okay, so to include this file here, okay, this IO def, because inside of this file you already initialize all of this what we call IO register with the value, okay, with the address, IO address. So later you're going to use the address. Okay, inside of going to use the address, you want to just what we call here, call a name of that address. Okay, so what you're going to do is you just include that file to your program by using the dot include. Okay, and then you have this symbol here, iodef.asm. So this is your file name. Okay, so you include this file. Okay, later if you write down in IRO's srec, you know that you're going to read from address 3f and then put to your RO. Okay, let's say lah, if you forgot to include this file, what happen after you execute this instruction? Apa yang akan berlaku? Okay, you will encounter a error. Okay, an error occurs here because the CPU doesn't know what is the srec because you not defined. Okay, kalau kamu terlupa, if you forget to include this file iodef.asm, what happen is, okay, when the CPU going to execute this instruction, and then the error will occurs because the CPU doesn't know what the srec value. Okay, unless you define the srec value, okay, on top of your program. For example, .equ srec ox3f, then this one will become valid again. If not, okay, so the error will occur. Okay, so when including this file in the assembly program, all IO register name and IO register bits appear in the data book can be used. Okay, so every time you include this file, for example lah, for ArtMega32, we need to include this file here. Okay, the file name is mt2dev.inc. So every time you go, okay, so all the IO register name and IO register bit names appear in the AVR books can be used. So you no longer need to know the IO register addresses. Okay, you can use the names. Okay, so this is saya padam dulu. Erase this one here. Okay, so this is the mt2dev.inc. This is the what we call here. Okay, the content inside of your mt2dev.inc, which is inside of this file here. You can see here you already initialize all the IO registered named with the IO register addresses. Okay, for example, this one here, .equ srec equal to 3f. You know that your status register, okay, location is dekat 3f, and then .eq spl equal to ox3d. So you know that the spl address is at 3d, and .eq sph equal to ox3e. You know that the sph, your stack pointer high, located at this address here. Okay, so all of the 64 IO registered will be defined inside of this mt2dev.inc file. Okay, so later when you write down your program, okay, you just need to include this file, okay, to use the names, okay, the IO names, okay, IO register name. Okay, so just include, Okay, at the top of your program, you just include m2def.inc. So every time you're going to write a program, so you no need to know the IO addresses. Okay, instead you can use the IO register names. Okay, so this is the m2def.inc file. Okay, you can see all of the what we call the IO registers have been initialized with the addresses kat situ. Okay, any question? Ada soalan tak up until here? Okay, if no question, next we go to the .org. Okay, so .org used to set your program origin. Okay, this one here you're going to set your program origin. Okay, if you put the .org under the data segment, means that you're going to set your program, your data segment address started at this address. Okay, if you put the .org dekat ESET, it means that you're going to set your EEPROM location at this address. Okay, if you put the .org inside of your code segment, you means that you're going to store all the instructions starting at this address. Okay, so this is what the .org do to set your program origin. Okay, next we have a .byte. Okay, so this one also commonly used, okay, in the programming. So this .byte used to reserve a byte to a variable. Okay, so the .byte directive reserves memory resource in the RAM. Okay, so in order to be able to refer to the reserved location, the byte directive should be preceded by a label. Okay, before you reserve, you need to give a name lah to that reservation. Okay, the directive takes one parameter, which is the number of byte to reserve. Okay, so this directive can only be used within a data segment. You see here, okay, the .byte only can be initialized, only can be used inside of your data segment, which is under your .dset. Okay, so for example kat sini, okay, let's look at this example. Okay, first you name that what we call here, you name the location that you're going to reserve. Okay, you give a name to the location that you're going to reserve. For example, this one here, you give it a var1. Okay, .byte1. What happen is you're going to reserve 1 byte to your var1. Okay, and if you put something like this, means that table.byte tab size, means that you're going to reserve tab size. Okay, you need to see lah what is the size of your tab size. Okay, to your variable table. Okay, let's look at this example. Okay, so hopefully this example here you can see more clear what the .byte do. Okay, so first we started with the dseg, which is this your data segment. Okay, so your data segment actually inside of your RAM. Okay, so we look back. Okay, kita recall balik semula. This is our data memory. This is your GPR. How many GPR you have? Ada berapa GPR? You have a total of berapa GPR? Anyone? Okay, you have total of 32 GPR, which is starting from address 0000 until berapa ni? Who want to help? Siapa nak tolong kat sini? Until what is the end address of your GPR? Anyone? Okay, 001F. Okay, use the formula. Start address Okay, the formula is for the end address sama dengan start address plus capacity minus with 1. Okay, so this one here 001F. 001F. This is belong to your R31. So this is R0. Okay, then you have a IO registers. So how many IO register do you have? Ada berapa IO registers in Atmega 32? You have 64. Okay, what is the starting address? Starting from 0020 until 005F. Okay, and then you have RAM. So this is your RAM. Okay, what is the starting address of your RAM? Starting at 0060 until, okay, your RAM size is 2 kilobyte. 2 kilobyte. You have 2 kilobyte of RAM until this is your RAM N 00085F. Okay, we call it as a RAM N. Okay, so by looking at this one here, okay, so this is your data segment. Okay, data segment actually is your RAM, which is starting from this address 60 sampai 085F. Okay, by right, if you don't put any origin.org here, means that the starting address of your RAM is 60. Okay, so we look at this one here. num1.byte1 means that you want to reserve 1 byte to your num1. So what happens is your num1 declared as a 1 byte storage by default at address 60. Why address 60? Because you not started with any origin. Okay, so by default, the starting address of your RAM is at dekat 0060. Okay, so you will reserve 1 byte to your number 1. So num1, okay, dia punya address is dekat 0060. Okay, next num2, okay, dot byte 1 means that you're going to reserve 1 byte to your num2. So num2 will be reserved at location 0061. Okay, let's say lah, I change this one here to byte 2. Okay, data 1 byte dot byte 2 means that I want to reserve 2 byte to my data 1. Okay, so what happen is my data 1, okay, I will reserve my data 1 at location 0062 and 0063. Why? Because this is 2 byte. Okay, because I want to reserve 2 bytes kat situ. Okay, let's say lah I put this one here. Okay, data 2 I want to reserve 4 bytes. So what happened? So my data 2, okay, I will reserve at address 0064 0065 0066 and 0067 because I want to reserve how many bytes? 4 bytes. Okay, so this is how you're going to reserve a memory location. You want to reserve a storage from your RAM. Okay, contohlah kalau this one here, okay, we just follow the what we call here the example kat sini. Okay, so what happen is, okay, so this one another 1 byte to data 1, so that's why your data 1 dekat address 62 saja, and then another 1 byte to data 2, so that's why your data 2, okay, is declared at address 63. Okay, see here, declare at address 63. And then you see here, numbers 2. Okay, numbers 2, you're going to reserve how many byte? 7 byte. Okay, so this one here. Okay, so numbers 2 will be reserved at location starting from 0064, 65, 66, 67, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 5, 6, 7, 8, 9, 10, 11, 12, 6 and 6 A. 1, 2, 3, 4, 5, 6 and 7. Okay, so this is your numbers 2 location. Okay, which is you started at 64 to 6A. Okay, so total of 7 bytes. Okay, and then you see here. Okay, kita tengok kat sini pula. .org ox8t and then numbers 3, you saying that you're going to reserve how many bytes? 6 bytes. So what happened? So to your numbers 3. Okay, since you have the origin kat sini, okay, since you started with the origin, means that now you're going to start reserve at location, starting location 00x0. Okay, so numbers 3, okay, will be reserved dekat address 0080 0081 0082 0083 0084 and 0085. 1, 2, 3, 4, 5, 6. How many bytes? 6 bytes. Okay. Any question? Okay, contohlah kalau kat sini. Okay, let's say lah. Okay, so this is my D6. Okay, previously no origin, so now I want to put the origin. Let's say like I put this one here become .org ox200 for example. So what happened is my number 1, okay, I reserve 1 byte to number 1, so the address here no longer dekat 60, which is starting address now dekat 200. Okay, because why? Why? Because I started my origin dekat 200. Okay, Josh asking that how this num1, num2 and etc. are used in the programming. Okay, so later we will see what we call here. Okay, later we will see how we are going to use this data reservation inside our program. Okay, we have an example for that. Okay, Chua Shin asking that is the number 1, num2, data 1 all is dot set before this? No, tak. Okay, we not declare the num1, num2, data 1 with dot set. Okay, before we writing this program. Okay, we just put here. Okay, num1 dot byte 1 means that we know that we're going to reserve 1 byte to our num1. Yes, I did I record this session. Okay, and later I will upload in the YouTube. Okay, any other question? Okay, Tan Yi Kwan asking if num1 is reserved with byte 1, is it possible if the data storage inside is more than 1 byte? Yes, it is possible, depending on your programming. Okay, what happens if the same address is repeated reserved? Okay, only one address can be reserved at one time. Tak boleh repeated reserve. Okay, exceed the capacity. What you mean by exceed the capacity, Tan Yi Kwan? Is it exceed the 085F? Or is it exceeded the one that we already reserved? The byte we already. Okay, okay, it just override if you okay, if it is exceeded the byte that we reserve, it just override to the next address. Okay, it will be saved to the next address. Okay, never mind. Later we will see the what we call here the example. for this one. Can the num1 allocated storage be changed? Cannot. Okay, you cannot change the num1 allocated. Okay, unless you do the correction in your programming and then you recompile. Okay, then you can change lah. Okay, then we have the .db. Okay, so this one here, define a constant byte in a program memory or EEPROM. Okay, so I just skip this one because it involves the EEPROM. Okay, .dw also define a constant word in program memory or EEPROM. So this one also I will what we call here, skip this one. Okay, then we're going to see the .def. Okay, so what the .def do, you're going to set a symbol name on a register. Okay, so this one you're going to change your register to a label, to a name. Okay, you fed up using the R1, R0, R32, R21, R16. Okay, you're going to use a fancy name, for example. Okay, you're going to replace the R16 with other names. Abu, for example. Okay, so you can use the .def. Okay, so this is an example, yeah. .def temp R equal to R16 means that every time you see the word temp, the label temp, you know that is belong to R16. Okay, .def IOR R0 means that every time you see the IOR, you know that is belong to R0. So this one on the .def used to change your register, your name of the you're going to change your GPR to a label or to a name, or you want to give a name to your GPR. Okay, then we have the .exit. Okay, so this .exit used to exit the file. Okay, so this the exit directive tell the assembler to stop assembly the file. Okay, normally the assembler run until the end of the file. Okay, so this one you put inside of your what we call here, inside of your file lah. Okay, so before you end your file, you need to put the .exit so that the CPU know that you're going to exit that file. Okay, so that is the assembler directive that available. Okay, that you need to know for the AVR assembly programming. Okay, so let's look at this what we call here example here. Okay, so you are given what we call a program, a set of programming. Okay, assembly programming. So now you are going to determine the value of register and memory after all the instructions are executed sequentially. Okay, so you need to find out what is the R16, R17 to R90 values, as well as 300 and 301 memory address value. Okay, so how to do this one? Macam mana nak buat? Okay, so first, what you're going to do is we need to see line by lines lah, from top to the bottom. Okay, so the first one here, this one, .include m32def.inc. What this instruction do? Okay, so this one here, you're going to include m32def.inc file to this program. Okay, and then .org0, okay, means that, okay, so this one, you know that this one here, you're going to start to origin your program dekat address 0, and then you see the jump start. Okay, so this is a jump start, dia akan lompat ke start, which is here lah. Okay, so under the start, you see here, .org200 means that this instruction here will be stored dekat address 200 because this is your instruction. Okay, so the instruction will be stored inside of your program memory. Okay, So this is the directive dot EQU thumbprint equal to F5. So every time you see the thumbprint, you know that this one is the value of thumbprint is F5, and then you see dot set rembao. Every time you see the word rembao, this one belong to FF. Okay, so the rembao value will be FF. Okay, and then next LDI R16 thumbprint plus 2. What happened here? Okay, you're going to load value, okay, which is thumbprint plus 2. What is thumbprint plus 2? F5 plus 2, and then put to your R16. So what is our R16 value? Okay, so F7. And then load I R17 rembao plus 4. Okay, what happened here? Okay, you're going to add, okay, so what is a rembao? Rembao is FF plus with 4 and load to your R17. Okay, so what will be your R17 value? Okay, the R7, okay, so when you add FF plus with 4, okay, you convert this one to hexadecimal, okay, because this is no, what we call here, this one here, no symbol in front of this value, so this is a decimal value, so you need to convert to hexadecimal. So 4 convert to hexadecimal, so it becomes 4 as well. FF plus 4, you will get 103. Okay, but bear in mind that your R17 size is how many bit? Berapa bit R17? 8 bit. Okay, so we just need to take this value and put to your R17. So 03 will go to your R17. Okay, next we have the dot set. Okay, Yanil, please put dot, yeah. Dot set rembao F4. Okay, so now rembao no longer have value FF. Okay, you change the value to F4. Okay, so every time you see the rembao after this instruction, what happens is your rembao become F4. You know that the rembao is F4. Okay, so LDI R18 rembao plus 8. Okay, so what happened to your R18? Okay, rembao sekarang no longer FF, yes? It have a new value F4. So F4 tambah dengan 8, you get F. 84 is 12. 12 is A, B, C. F, C. So this one become FC. Okay, next LDI R19 thumbprint plus 7. What happened to R19? What is the value that will be load to your R19? Okay, thumbprint. What is a thumbprint? Thumbprint F5 plus 7, you get FC as well. And then next, STS 300 thumbprint. So what happened to, okay, what you're going to do here? STS, what this instruction do? You're going to store, okay, the value. So I think this one is STS thumbprint. Okay, I think this one is wrong lah. The syntax is wrong actually. Okay, you cannot put the, okay, because the syntax for STS is STS, and then this is your K, and then this is your RR. Okay, you need to, okay, this one cannot numbers. Okay, cannot a constant number. Okay, it should be your register. Okay, let's this one here kita tukar lah. This one instead of thumbprint ya. Let me check for STS, STS, ST, STD, ST, SKEE. Okay, so we just put this one F7. It is 03, and this one is FC, and this one is what we call here FC. Okay, let's lah this one instead of thumbprint and rembau we change to saya tambah kat sini def thumbprint 1. Okay, so let's change this one. Ini salah ni. Not highlighted. Okay, let's I put something like that. Okay, STS 300 thumbprint 1. Okay, why? Okay, what is the value that you're going to store dekat address 300? Okay, I already put here, I already defined that .def thumbprint 1 equal to R18. So every time I see the word thumbprint 1, it belong to R18. So what is our R18 value? R18 is FC. So FC I will put to my 300. Okay, next. SDS 301 rembau 2. Okay, what is a rembau 2? Rembau 2 belong to R17. So what is my current R17 value? So 03. So 03 I store dekat address 301. Okay, so list down 4 assembler directive that can be obtained from program 1. Okay, what is the assembler directive that you can obtain from this program 1 here? Okay, first, can you tell me what is the assembler directive that available in this program 1? Okay, dot include, and then you have .org, .equ, and then .set as well as your .def. Okay, any question? Okay, so this is the kind of question that will be asked in your test as well as in the final exam. Okay, so let's look at this one here. Okay, you're going to analyze the following program. Determine the final value of register and memory stated in the question. Okay, the instructions are sequentially executed. So 20 marks. Okay, so later you need to find out what is the value of R16, R17, R18, 90, R20, as well as the memory, the value, the content inside of memory address 60, 61, 62, 63, and 64. Okay, I give you 10 minutes. Okay, to solve this one. Okay, doctor, was .org 200 executed or skip? Okay, this one actually it is executed. Yang ni executed because this one yang started at sini sepatutnya. Supposedly the start address is dekat sini. .org 200. Okay, can you do this one? I give you 10 minutes. After that, what we call here? We'll discuss the answers. Okay, this one here. So you see here, kat sini. Okay, this one involves the .byte. Okay, the reservation of your memory address. Okay, .byte. Okay, if the start is below 200, mean it will skip? Yes. Okay, because you ask, okay, contoh lah, for example lah, okay. For example, I put the start dekat sini. Okay, for example lah, this start here align with the .equ means that you skip this instruction because you ask the CPU to go to this start, which is here. Okay, so the instruction for .org 200 will be skip. Okay, so we continue this one. Okay, so if we remove the jump start, will the program have error? In this case, no error. Okay, you can remove the jump start. For this program, there will be no error. Right, so this is the initial value. Okay, given the initial value of your register R16 until R20, as well as your memory address starting from 60 to 64. So this is the content inside of this memory address here. Okay, so this is the program starting with .org 200 means that all of this programming will be stored, okay, will be started at 200 inside of your program memory. Okay, next, .set count 24. Okay, so every time you see the word count means that the value is 24. Okay, bear in mind that this one here 24, no symbol in front here means this is decimal value. Okay, and then .equ aku equal to 02 means that every time you see the word aku, it is 02. So this one also no $ symbol or 0x symbol, 0b means that this is a decimal number as well. Yes, and then the first instruction here, load I R16 count. So what happened here? R16 will have what value? Okay, you're going to put count, which is 24, to your R16. So what is your R16 value? Is it 24? Anyone? Okay, so 24, you convert to hexadecimal, so you will get 1818. So gantikan di sini, it become 18. Okay, and then load I R17 count divided by 3 means that 24 divided by 3, which is you get 8, and then put the value to your R17. So R17 will have 0808. So this one change to 08. No. Okay, you see here all the contents. Okay, so Lim Junji asking, is it compulsory to convert to hexadecimal? Yes, you need to convert all the answer in hexadecimal. Why? Because you see the content of your register as well as the content of your memory always in the hexadecimal number. Okay, so you need to convert all this value here to hexadecimal value. Okay, why? Because later this value here you need to put inside of this table. You need to fill in this table with this value. That's why you need you need to convert to hexadecimal. Okay. Okay, and then is it the decimal is the answer in decimal is acceptable? Okay, in this case, if you give the answer in decimal, then your answer will be wrong. Definitely wrong. Okay, you get 0 mark for that. Okay, next. Load I R18 count. Okay, and then you have the star 2 means that you're going to count multiply with 2. So 24 multiply with 2 you equal to 48. 48 convert to hexa. So R18 we have what value kat situ? 30. Okay, and then load I R19 count plus 4. Okay, 24 plus with 4 you get 28. 28 you put to R19, so convert to hexa you get 1C. Okay, so tukarlah kat sini. So this one also you need to tukar lah. Okay, so this is 30 and this one is 1C. Alright, and then the last one here for the load I is R20 count minus 15. So 24 minus 15 you get 9. 9 convert to hexa. Okay, so R20 equal to 0, 9. Okay, next. Okay, so next you see here SKS Lela, SKS Amin plus aku, SKS Rossi plus aku. Okay, for this part here, okay, what you're going to do is, okay, you need to refer to this data segment. Okay, the one that you reserve inside of your data segment. Okay, so first we look at Lela. Okay, so Lela, you reserve 1 byte. So what is the starting address of your Lela? Lela 1 byte. So what is the address that you reserve to your Lela? 60. Why 60? Because you don't have any origin. Okay, you not initialize with any origin. So by default, it is 60. Why? Because your RAM starting at address 60. Okay, inside for Atmega 32. So this one is 60. 60. Okay, then you have an Amin. Okay, so you reserve how many byte for Amin? 2 byte, which is dekat address 61 dengan 62. This is for Amin. Okay. And then you have a Fadi. Fadi, how many byte you reserve for Fadi? 1 byte. So the Fadi you reserve dekat address 63. Okay, and last but not least, Rossi. Okay, so I put Rossi here. So Rossi, you reserve 2 byte. So the Rossi you reserve at address 64 and 65. Because 2 byte you reserve for this Rossi here. Okay, next. Barulah kita answer this question here. Okay, we look at this instruction. Okay, STS Lela R16 means that you're going to put R16 value to your Lela. So what is your Lela? Lela is 60. Okay, at address 60. So you put value R16 which is 18 to your Lela. So sini akan dapat 1, 8. Okay, so I put kat sini lah. Okay, so Lela is 60. Okay, at address 60 you have 1, 8. Okay, next. STS Amin plus aku. What is your Amin? Okay, your Amin starting address dekat at 61. Okay, so 61 plus with aku. What is your aku is 2, which is 63. Okay, so you go to address 63. Okay, so this one here, this is address 63. And then you store value from R17. So what is value from R17? 08. Okay, 63 now have 08. 08. Okay, next, ROSI. What is your ROSI? Okay, so ROSI is you reserve dekat address 64 and 65. Okay, so we take the starting address, which is 64. We started at 64. Plus with aku, which is 64 plus 2, you get 66. Okay, so at address 66, what you going to do? Okay, you store value from R18. What is the value of R18? Which is 30. So address 66, okay, which is somewhere around here, sama dengan 30. Okay, next. STS ROSI R19. Okay, so what is your ROSI? Okay, you have two reservation for ROSI. One is at address 64, the other one is address 65. So we take the starting address, which is 64. Okay, so dekat address 64, and then you're going to put R19. What is your R19? 1, C. So address 64, so this address 64 now become 1C. And then the last instruction here is LDS FADI minus 2. Okay, so what is the address that you reserve for the FADI? FADI is 63. Okay, 63 minus with 2, you get 61. Okay, so at address 61, is it correct this one here? Okay, salah ni, terbalik ya. This one is terbalik. Okay, the instruction is wrong. Okay, actually, okay, LDS R20 FADI minus with 2. Because you're going to load the value from your memory space, okay, or your data memory to your R20. So this one is wrong. Okay, please correct it to LDS R20 FADI minus 2. Okay, you can refer to the instruction set summary that I give you earlier. Okay, so every time you going to answer this kind of question, so you need to refer to that instruction set summary. Okay, no need to what we call here, no need to remember each of these instruction. Okay, because why? Because you can refer to your instruction set summary, either in your exam or in your test. Okay, the instruction set summary will be provided to you. Okay, so dekat address 61. Okay, so what is the address 61? Which is 67 lah. Okay, so 67. And then what happened is, from address 67, you load to R20. Okay, so now this one here, instead of 09, dia akan tukar jadi 67. Okay, and then you fill in this table. Okay, while the rest, you just copy back the answers. And you get 20 marks. Any question? Ada soalan tak? Okay, it's a situation where Amin will have both byte get affected. Amin, both byte get affected. Okay, contohlah. Okay, if you're going to, okay, so this one here. Okay, because Josh asking that, is there any situation where Amin will have both byte get affected? Okay, I put another instruction here. Okay, because we're going to see for the Amin here. Okay, so STS Amin plus 1 R17. Okay, so what happens is you're going to store value for R17 to Amin plus 1, which is Amin. Okay, you reserve dekat 6162, so Amin plus 1 is 62. So you store at this address. Okay, question from Tan Yuquan. Okay, can you explain again why start at address 60? Okay, kenapa kita start at address 60? For Leila, Amin, and Fadi here. Okay, for the Leila here. Kenapa address 60? Okay, recall back. This is your data memory. Okay, so this is your data memory. Nampak tak? Okay, so this is your GPR. This is your IO. And this is your RAM. Okay, so this is your data memory. Okay, then you have a memory address called data memory address here. Okay, starting from 0000 until your RAM end. Okay, since this one here, your GPR, you have 32 total of GPR. So your starting at the end address of your GPR is 001F. Okay, starting from the starting address 000 sampai 1F. Okay, total 32 GPR. Okay, and then next IO. Okay, the starting address of IO is 0020 because this is 1F. You plus with 1, you get 20. And then this side you have a 64 byte of your IO register. You have 64 IO register. So the end address of your IO register will be 2F, 5F, 005F. Okay, total of 64. And then the RAM started at 0060. Okay, because in this one here, okay, you don't put any origin.org, so by default your RAM started at address 0060. Okay, so Chan Kainto asks, for final answer for the memory, we need to do until 64 or 66. Okay, for this question here, okay, only you need to, okay, because below at the bottom of this question, it asks you to fill in this table. Okay, so you just need to put the value, the content for this table only. Okay, up to 64 only. Tak sampai 66. Okay, and then the other question by Josh. How to know that the D segment get executed before it does the STS instruction? Alright, so by right, this one here, the data segment selalulah, usually, okay, we put it at the top of our program. But you also can put it below bottom here because the CPU, because why? Because before the CPU, what we call here, the CPU run this program, okay, you're going to convert this program to machine code. Okay, so what happens is, okay, so once you convert this program to the machine code, so the CPU already know that, okay, so this one here you already reserve, you already run the data segment, means that the CPU know that you're going to reserve this one. Okay, what is the value of 61 in memory? Masih lagi 67. No change. Okay, the value of address 61 still 67, whilst the value for address 62 masih lagi 52. Masih lagi yang sama. No change. Yes, correct. Josh. Okay, means that the data segment and code segment, the CPU write in simultaneously. Okay, because one inside of your RAM, the other one inside of your program memory. Is the value 62 and 62 is same? Apa ni? Is it value 62 and 62 is same? What you mean by value 62 and 62 is same? What you mean by 62 and 62 is same, Khalid? (62) and 63. Okay, 63, the value is 08 eh. Okay, while the 62, we copy back the previous value. Previous value for 62 berapa eh? Tak nampak lah sini. I dah conteng. Okay, 52. Okay, so kat sini I put back. Okay, 62, dia punya value is 52. While 63, 63, the value is 08. After you execute this instruction. Okay, are we going to do this another example here? Because this is the last slide of module 4. Okay, let's look at this example and then we finish our class. Okay, so and then on Wednesday we continue with new chapter. Okay, so this is the last slide of our module 4. Okay, so let's look at this example. Okay, I give you 10 minutes. Okay, to get the answers and then after that we do discussion. Okay, so you're given this program with the what we call here register value and memory address value. Okay, then you're going to find what is the value of your register after you executed these programs. Okay, so what you need to do is, okay, first, okay, so this is the initial values of your R0, R20 to R31, and this is the value. Okay, you see here the value is in the hexadecimal. Okay, starting from address 300 to 305. Okay, so this is your code segment and this is your data segment. Alright, so let's look line by lines. Okay, the first one here, .org OX100 means that all of this instruction here will be stored dekat this instruction here will be stored at starting address hundreds. Alright, and then .dev temp R21. So what happened here? So now you're going to replace R21 with name temp. Okay, every time you see the temp means that it's belong to R21. And then EQU value. Okay, so this is the value. Every time you see the value means that the value of, okay, the content of this value here is 0B10100101 or in hexadecimal is A5. And then .set count 45. So every time you see the word count means that it have 45 decimal. Okay, so let's look at this. The first instruction, load item 55. So what happened here? Apa yang berlaku kat sini? Okay, so you're going to load number 55 to your temp. What is your temp? Temp is your R21 lah. R21, you're going to put number 55. But since this one here, this is in decimal, your R21 is hexadecimal. So what is the value of your R21? Okay, 37 ya. So this become 37. So R21 sekarang ni tukar kepada 37. Alright, and then the second instruction, LDS R22 number 1 plus 1. Okay, so this number 1 plus 1 you see here. This number 1 plus 1 here belong to under data segment. Okay, so you're going to find out what is the location that you reserve to this number 1s and numbers 2. Okay, so this is your data segment. Origin 300 means that your number 1 started to be reserved at address 300. So this is number 1. Saya letak kat sini. Numbers 1 reserve dekat address 300, 301 and 302. Why? Because you reserve how many byte? 3 byte kat situ. Okay, and then follow by my numbers 2. Okay, so this is numbers 2. Okay, so starting at address 303 and then address 304. Okay, why? Because you reserve 2 byte dekat number 2. Okay, so LDS R22 number 1 plus 1. So the starting address of number 1 is 300 lah. Okay, so you add with 1. So this is become 301. So at address 301, what happen is you get the value and put to your R22 because this is your LDS. Okay, load from memory or data memory space. Okay, so the address 301, you go to this address 301, which is here. Okay, take the value and put to your R22. So R22 sekarang ni ada nombor D7. Okay, all of you get D7 for the second instruction here. Semua dapat D7 tak? Yes. Okay, great. Okay, next. SUBI. Okay, so what is the SUBI do? Apa yang SUBI buat? Okay, you're going to subtract R23 with an immediate value. Okay, which is your immediate value coming from count minus 5. So what is your count? Count is 45 minus with 5, which is yang ni you can replace it with 40. Okay, so sub I R23. What is your R23? BC minus with 40, but bear in mind this is decimal, so you need to convert to hexadecimal. So 40 tukar dalam hexadecimal, you get berapa? Okay, so 28. Okay, so this one is 28. Okay, so BC minus with 28 and then your R23 sekarang ni will have, what is the result of R23? 94. Okay, correct. Okay, so tukar this one, so this is become 94. Okay, so we finish this one. And then next, STS number 1 R23 means that you're going to store value from R23 and store it to the number 1. What is your number 1? Static address 300. So you get the value from R23, which is 94, put to address 300. So this one here become 94. Okay, so I put lah kat sini. Okay, so dekat 300, address 300, you put 94. Okay, so up until here. So far so good Semua dapat Alright, the next instruction. Load I R30 low number 2. Okay, so load I R30 low number 2. What is number 2? This is your number 2. 303. But since R30 is 8-bit, but okay, R30 is 8-bit, but this one here, it is 16-bit. So you can divide it to low byte and high byte. So this is low and this is high. Okay, so dia kata kat situ load I R30 low. So you get the low from number 2, which is 03, put to R30. Okay, so what happen is after you execute this instruction, R30 now will have 03. Okay, so 03. So see, this is R30. Okay, and then load I R31 high number 1. So you get the high, which is 03, put to R31. So this become 03. So what happened is, so actually R30 and R31 is your Z pointer register. So now your Z pointer register point to what address? 0303. Okay, and then barulah you can do this instruction STZ plus temp. What happen here? Apa yang berlaku kat sini? Okay, you're going to store value from temp, which is R21, to the address pointed to by pointer register Z. And after that, your Z will increase by 1. Okay, so what is the address that pointed to by your pointer register? 303 lah. Okay, so 303. Okay, and then you store your temp. What is your temp? R21, which is 37. Okay, so dekat 303 sekarang ni you replace this one with 37. And then what happened to your Z pointer register Z? Your pointer register Z will increase by 1. So now it point to 304. Okay, so yang ni I change from 03 to 04 kat situ. For R30 ya. R30 now no longer 03 because you already increased by 1, which is 04. So I change R30 to 04 while R31 remains lah 03. And then what are you going to do? Okay, then we do the next instruction ORI R20 value. Okay, so you're going to do, what is ORI? You're going to nak buat apa ni? Do logical OR with an immediate value. So R20, what is your R20? 000. So 0000. And then what is your value? Value is this value 10100101. So 10100101. You do the logical OR and then you get the same value lah because you do the OR with 0. So kamu akan dapat 10100101, which is equivalent to A5. Okay, so what happened is now R20 sama dengan A5. So tukar this one become A5. Okay, and then the last instruction here is STZ-R20. So you're going to store value from R20 to the address pointed by pointer register Z. So your pointer register Z point to what address? 0304. Okay, so you store value from R20 to this address 304. So sekarang dia akan dapat A5. Okay, so this is the table. Okay, for address 301, 302 and 305, so you just copy back lah the initial value. Okay, and then you get 11 marks. Any question? Ada soalan tak? Okay, if no question, then I think we'll stop here. Okay, so Wednesday we'll continue with module 5. Okay, thank you class. Okay, make sure you sign the attendance.